Hello folks in 113. Today we're going to be starting with chapter 9, right? Specifically just section 9.1. Where's the calendar? Makes me feel better when I do this, thank you. Being patient with me. Today is April Fool's Day, yay, right? And here's the biggest fool of all. Thursday, April 1st. Alright, so we are, according to schedule, are covering section 9.1. Today's Passover, and then there's Easter Sunday following it. Good Friday's tomorrow. Alright, any other holidays? If I neglected to mention them, do forgive me. Anyhow, it doesn't have any bearing on us, but we technically have off tomorrow. Alright, let's see. Okay, now the packet that I have for you today looks like this. I swiped a lot from the textbook this time. These yellow sort of rectangles are very useful. I left in some of the descriptions above and below them because they seemed helpful. But in case you're not watching this video, at least you have this. You could definitely figure this out for yourself. You have to trust yourself that you can. Okay. Nonetheless, my job is to partially digest this for you. This at the end is very useful as well. All right. This is a standard that you will follow for criteria to decide whether something classifies as being a group or not. All right. Just fair warning. The material that you're going to see today and forthcoming 9.2 and 9.3, it's a little alien. I wouldn't call it practical math. It's still useful to us as a mental exercise, and that's really why we're going to do it. Okay? But if at first you don't really feel like you've assimilated it, don't feel bad. That is only natural. All right? Eventually, if you do anything enough times, it will make sense. All right? You have to sort of forget the things that you know and just start with a blank slate, at least largely. I'm going to leave in a sheet like this as well because I want to give you a list to clarify some things, the criteria for being a group, right? And then there are 3 examples. I left the solutions here because it explains them. Okay, and that's that. All right, so if you're following along, print this out and I'll try to dissect it. Let me give you this. Time is running good. Alright, I drew this badly drawn triangle just to indicate that if you want to, just to separate out your notes, fold over corners, right, and then you'll have a partition. But just doing section 9.1. This is the plan for chapter 9, which is only 3 sections. All right, it's going to consist of these parts, and I'll keep reiterating this. All right, chapter 9 will consist of section 9.1, which we're doing today, section 9.2, and section 9.3. Okay. All right. Section 9.1 is about something called mathematical systems. Realistically, and in contrast to what's coming, these will be what you might regard as infinite systems. You don't really have to dwell upon it too much today. The alternative. All right. The forthcoming section 9.2 is math systems again. Really abbreviating in this case, but there'll be the finite example. All right. Meaning that there's a limited limited set. All right. This is a pardon me, that's not a word. This is revisiting the subject from earlier, which is sets. Remember in sets you see fancy braces often, right? and it's basically a container for numbers, right? Now, if you have an infinite set, as this will definitely incorporate that, it will be dealing with a concept like natural numbers. Natural numbers will go on forever. You could keep counting, right, indefinitely, right? So, whereas a finite set would be something that is limited between one number and another number as a boundary, right? What we'll eventually get to, I don't know if I trust green, but is something called modular arithmetic. And if you've never heard that term before, don't feel bad. Again, this is a little bit alien hieroglyphics for the moment, right? Again, the value of doing anything, even if it's not immediately practical, is that it's a mental exercise. And the mental exercise, more so than the actual solutions to any particular problem, is what makes you smarter. So we're going to keep an open mind, right? And we're going to make sure that we have this experience, right? The experience is, as often the case, the most important thing. All right. This has a lot to do with notations. There's abbreviations is what I'm getting at. Right. What you're going to see in section 9.2 is there'll be a lot of tables, and you learn how to read the tables. All right, little tricks to the trade. All right. Anyhow, this is the future, and this is right now. All right, we're going to be discussing mathematical systems, the concept in general. All right. All right, there's an overview. I'm being texted. I shouldn't be. I'm not going to wolf. This is an overview of the next couple of days. As for the material, here's what we're doing now. All right, you're going to be hearing phrases like this. Well, firstly, mathematical system. That's a bit faint, sorry. This is a new mark, I swear. Okay. Mathematical system, all right, and a subcategory of that would be a group. And then eventually there'll be this other category, which is sort of an offshoot of it. I've had enough of this now. I gotta turn off my phone, I'm sorry. Alright. I'm getting distracted, I'm sorry. This is the concept, when you hear this phrase, this is a generalization, right? We have what is referred to as a mathematical system. A mathematical system is essentially a set, right, whether infinite or finite, right, which means that there are elements in it, in the set. That usually means numbers. All right, and what they call binary operation. At least one technically, but you're not likely to see more than one. A binary operation is when you apply an operation to two things, right? So what that usually means is multiplication or addition. Right? Doesn't have to be exclusively those things, but that's what you're likely to see. Right? So you have some set of numbers, that is the parts to work with, and then you have the operation, the thing that you do to the numbers. Right? And this is a generalization to say a mathematical system. If you are a little bit more specific, all right, then you might have a group. Right? Now, there's not a lot of space here, and I'm going to give you a worksheet in addition to whatever the explanation is that is on the handouts. But just to give you a heads up, this is a mathematical system that meets 4 criteria. Four requirements. We need to basically take the time when we get there to discuss what these 4 requirements are. But for right now, just realize that in order to qualify as a group and not simply some mathematical system in general, if you want to be a little bit more specific, you have to follow a stricter criteria. So there'll be 4 requirements. When it comes to a commutative, or otherwise known as a Abelian group, after the person who was responsible for introducing us to this, there's a 5th criteria. So this is even more specific. Even more specific. This will be basically has a 5th requirement. Right, so that's basically the material that we're going to be covering today. Mathematical systems, examples of those, groups, how to judge whether something qualifies as a group or not, and then in the extreme case, whether or not it will cut the mustard as being a commutative or a Abelian group, right? Again, not immediately practical, it's really more an exercise in mental flexibility. Okay. Let me give you another diagram. I always hope this helps. I swear, this is why I do this. Start with this. I have to kind of confine myself as I often do. Hopefully this is sufficient. What I would do if I were writing this in a notebook is, fold over a paper in half and then fold the half in half so that you have quarters. All right, that's just if you want to. All right, I have to draw these sort of lines to partition my own writing, because I have a tendency, you probably noticed, to write sideways off the board. Anyhow, let's discuss other properties. Right. And by other properties, I mean things that are not associative, commutative, or distributive. Right? Those are the subjects of section 5.5. These will be important again later, associative and commutative specifically. But these are the things from section 5.5. So we're going to be discussing other properties, and there's basically two categories that we're going to consider. There are firstly the identity properties. Okay, and then there are inverse properties. What do identity property, yes, identity properties do? It's in their name. I'm just checking to see my camera's functional, good. Identity properties basically preserve identity of one of the elements that you're working with, one of the numbers that you're dealing with, right? These are things that we're basically giving names to something that you intuitively know anyway, right? So for example, there is famously an identity property, I'm just going to put this in singular form, of addition. And there is an identity property of multiplication, right? They still fulfill that requirement. They just do it in different ways, right? I don't know if this light is going to help me or not, but I will see. That is better, I hope so. I'm sorry for the glare too. Right. An identity property of addition will again preserve the identity of one of the numbers that you're dealing with, right? But it does so from the perspective, the operation of addition, right? Similarly, the identity property of multiplication preserves the identity, right, of one of the elements that you are working with, right? But from the perspective or the angle of multiplication. Okay, so here's the model that we tend to follow, and it is in fact available again in this packet. Yeah, it's there. It's just kind of buried a little bit. So anyhow, I'm going to use black because I think it might be a little bit easier to see. You know this again intuitively. 0 plus, I'm going to use the letter K, the lowercase a as in any element, right, is equal to what? Right? 0 plus anything is equal to what? Right? It's equal to that element. Right? This is an element, any element, right? It's equal to itself. 0 plus something equals itself, right? Essentially, right? That's preserving the identity of this element, right? Via addition, right? Here's multiplication, right? Similarly, you know this intuitively. 1 times anything is equal to what? That thing itself, right? This is any element. That is the result, right? 1 times anything is itself. 0 plus anything is itself. Okay? These two features, which are worthy of saving, I'm going to put a little box around them. 0 specifically, and 1 specifically in this case. These are important, right? You want to preserve them. These are known as an identity element. Again, for the reason that it preserves identity. Right? This is also an identity element. All right. They have specific names based upon whether it stems from addition or from multiplication. This would be called the additive identity element, and this would be known as the multiplicative. Anyhow, again, you know this intuitively, but we need to basically construct a model for reference later. All right, and we need to give a name, a special name, because this is going to be part of the criteria for qualifying as a group per se. All right, now over here, all right, for inverse properties, and again, I'm just going to put this in singular form here. All right, what is their job? Right, if you want to subscribe jobs here. They produce either a 0 or a 1. Right? They basically cause a cancellation effect. Well, they illustrate a cancellation effect. Okay? The result of them is that you either get 0 or you get 1. You get an identity element spit out at you. That is on the right side of equals if you're writing it. All right? So there is an inverse property, all right, again, of addition. And there is an inverse property of multiplication. Okay, and the models, which again, you most likely already intuitively know this, humor me, would be something like this, very general. A, again, as in any element, right, plus, and I'm going to somewhat reluctantly use parentheses now, plus the negative incarnation of it, right, results in what? Something plus its opposite magnitude self, right? It's the same magnitude, but it's an opposite sign. What do you intuitively know is going to happen, right? It produces 0, right? Right. So it produces either 0 or 1, and in this case, for addition, it produces 0, right? When you think addition, think 0, right, as the outcome. Right. Similarly, I should say related, is this. If you start with A as in anything, right, and you multiply by what we normally refer to as a reciprocal. Right? Remember, reciprocal is the sort of fancy way of saying something upside down. So if this was A over 1, you could write it in the style of an obvious fraction, in which case it would be 1 over something, 1 over A, right? What is the effect here? Again, it's sort of a cancellation effect, all right? Something times its reciprocal, all right? Maybe I'll put this in red, just to be consistent here. All right, is equal to what? All right, it's equal to 1, right? Again, this is the outcome in this case, as opposed to being something that's part of the process, right? This is part of the process. All right, and this is instead an outcome. All right. Anything times its reciprocal is equal to 1. There's another name for this, right? instead of saying reciprocals. This is often the case in math. There's more than one way to refer to something, in addition to more than one way to do something. The word you want to kind of keep in mind, right? This thing, this is referred to as a multiplicative inverse. All right, this is another type of inverse. It's just not the multiplicative type. It's the type that, again, originates from the operation of addition. This is known as an additive inverse. All right. So an additive inverse produces 0 in tandem with the original element, and a multiplicative inverse in tandem with the original element produces 1. They produce interestingly, the identity elements, 0 or 1. Okay. All right. That's a lot to swallow, granted, but just take comfort in this fact, right? You know this one way or another. As a person who's maybe 18 or older, all right, if you're in this class, all right, you've seen this at some point in your life. It's in here, all right? It's just finding a use for it now, all right? Anyhow, just bear this terminology in mind for the time being, okay? Let me free up some space. All right, let me pull this up. Little diagram scaffolding that I like to use. And we'll give you some criteria. There's a lot of preliminary information you could see. All right. So it is best to make sure that that is all nailed down nicely before we do examples. So let me turn on the projector here and adjust the lights. Okay, there you go. All right. I'm not used to it being this quiet. All right. What I want to do here is list the 4 or 5 requirements of being a group. It's 4 just to be a group in general, and then there's a 5th one. In theory, if we are a specific type of group, an abelian or commutative group. All right, what's the point of this stuff? Well, remember, a mathematical system, all right, that is something that is a set, an operation, all right, is more specifically a group, right, if it meets these 4 criteria. Requirements, I'm sorry, I'm kind of squeaking this in here. If it meets these requirements. Okay. I'm going to list them here. All right, hopefully this will fit. 1, 2, 3, 4, and then just because, for the sake of contrast, the 5th possible requirement, I'll put in red here, maybe a little asterisk to distinguish it, right? That's again if you are commutative group. has to meet that extra requirement. Okay. Now, what are the standards here? A mathematical system is a group if it is closed. All right, I'm just going to put under here, under the operation is the phrase that they use. Under the operation. Remember, it's usually adding or multiplying, right? You may or may not remember, it depends on whether you have the material from section 5.5 or you've seen it. Closure is a definition, all right? It's a property, all right? So just to reiterate that point, let me explain. Something is closed, all right, when the operation, which is usually adding or multiplying, results only in producing more of the same elements. Okay, there's certain words, you have to capitalize them because I want to emphasize them. If something is truly closed under a specific operation, and again, that operation is typically adding or multiplying, right? It is when an operation, one of these two perhaps, results only in producing more of the same element, right? Type, right? So for example, if you're dealing with natural numbers, 1, 2, 3, 4, 5, if adding them, all right, only results in producing more natural numbers, then we say that the group is closed, all right, or the system is closed. All right. The next one is this. All right. A mathematical system is a group if, all right, qualification number 2, it includes or it has the appropriate identity element. Right, it has to be appropriate for adding or subtracting, adding or for multiplying. So in other words, in your set, right, typically this is 0 or 1. This is for addition, right, and this is for multiplication specifically, right. If your set has a 0 in it, then it has an identity element. If your set has a 1 in it, it has an identity element in it. Now what you're hoping for is that you want a 0 in the case of the operation of addition, and you want a 1 in the case of the operation of multiplication, okay? I'm going to reluctantly use green. All right. A mathematical system is a group if it has the appropriate inverse. That's a bit faint, right? Oh, come on, green. It has inverses. I'm going to have to darken this if it's not visible. Let me look at my projection here. Can you see that? I mean, right on top of it, make it a little bit darker. Ugh, let's make it worse. It has inverses, and I really must say plural in this case because it would need to be several, probably. All right. Inverses for each element, right? Not just one, but all of them that are involved. Okay, so again, typically, what does that mean? It means typically the inverses would be a negative integer or a reciprocal, so 1 over a from before. Now just remember, if you have the appropriate, if you're dealing with addition as an operation, you want negative integers, right? So this is in a situation where you're hoping for this for each element, right? This is when you have the situation when your operation is addition, and this is in the situation when you have multiplication as the operation. Okay? And then there's this last thing, which I hate to say it, but you really can take it for granted a lot of times. A mathematical system is a group if it is totally associative. And I hate to say the word totally, but this is like, wow, rad, you know. But genuinely, this is really one of the requirements. It's totally associative. What do I mean by that? It means this is often given to you. It's often a given. Somebody will basically say, hey, listen, it's associative. Why? Because of it's tedious. Because of the tedium of having to check every possible combination of the elements, right? You could be, if you have quite a slew of elements, it'd be there for quite a while. All right, so it's not realistic, but do remember the associative property, all right, which remember involves 3 things simultaneously. You can make it more complicated, all right? All right, so when you have when the associative property is being engaged, right, it's really just an exercise in doing 2 particular things first, or 2 other particular things first. All right, so you'll see grouping, all right, on one half of an equation, all right. Or when you're checking, you just like you add 2 things first, and then you add a third thing second, or you switch them somehow. Right, that's for addition. Right, if it was multiplication, it's the same thing almost, except that you have operation of multiplication instead. So notice something. When you're staring at the contents of parentheses, there are 2 elements naturally, the binary operation applied, all right? And then they share 1 element in common, but not both, all right? Whether you're adding or you're multiplying, there is thankfully an associative property of addition and an associative property of multiplication. This is old hat, but here it is again if you need the reference. It's on the front page, okay? Now, the 5th quality requirement, right? If you were hoping that your group is in fact a commutative group, you would have to check yet a 5th standard, all right? And in that case, you might have guessed what it is, all right? If 4th is, your situation is totally associative, then, this would be the situation where it is also totally commutative. In this case, you would, in theory, have to check the commutative property, which is for addition is arranging your combinations of elements as a plus b, right? And then checking to see if you get the same solution if it's b in front, right? Or a times b, and then switching their arrangement a ba, right? This is again something that can be very tedious, right? But if you stumble across one example where this relationship is not true, all right, then it's not commutative. It might still qualify as being a group if you've met the 4 earlier requirements, but something may be a group and also not commutative. All right? So you would have to, again, you would have to check all possible combinations. So they might let you slide on that. You'll see. Okay? Depends on how many elements you have to begin with, really. All right? So you're aware you have 4 standards that you have to meet. All right? The good news is this. As soon as you hit an obstacle, you're done. All right? So like if you, let's say something is closed and it does involve an identity element, but then when you check for inverses, it doesn't have the inverses, you go, that's it. It's not a group, right? You won't bother continuing with anything beyond that. All right. Let's do some of the examples that are available here. Let me turn this off. I think it's a little too dark in here. I'm getting scared. Anyway, so I need light. Dracula needs light. All right. All right. Incidentally, the standards that I'm trying to outline here, again, they are available in this packet. Just to allude to it. If you don't like my explanation, and I would never get mad at you for that. Here you have the same 5, right, listed under the standards for a commutative group, right? Just realize that it's the extra standard to be commutative, so you would have to follow the first 4 and then the 5th, okay? All right? As a teacher, get in the habit, all right? Especially if you can't reproach yourself too much, but you should offer multiple pathways to the same destination. So if your explanation falls short for some of your students, trying to give them some alternative way. All right. This is why a good textbook, all right, is definitely a worthy investment. All right. A lot of times, like your principal or the person in charge will say, you know the subject. You don't have to worry about the book. That's not true. The resource that you choose, your textbook, is invaluable, all right? And sometimes you get a crummy textbook, right? So you may have to provide a better one on your own, right? In addition to your own experience, all right? After 10 or so years of teaching, you pretty much have figured out your style, all right, and what you feel comfortable with, and you've built up an arsenal of different techniques, right? So I'm going to take the examples right here and just kind of walk you through them. The solutions are there, all right? But what I want to do is, I didn't leave myself a lot of space. I'm going to translate the example and then explain the solution. Example 1, 2, and 3. All right. So here we have example 1. All right. All right, and it's a question of, all right, is the system that is, remember a system is a set, so I'm going to put whole numbers right under addition, right, plus sign for addition, right, a group. Right. Is this system, the system of whole numbers, it's a set of whole numbers, under the operation of addition, a group in fact. All right, so what do we need to do? I would illustrate at least a portion of the whole numbers. You can't obviously write them all, but start with that as a sort of preliminary step. All right. How does it look? All right, the set of whole numbers. Whole numbers include 0. They're not the natural numbers. They're the next logical concept. All right. Natural numbers start with 1. Whole numbers start with 0. Right? So it would be 0, 1, 2, 3. And you can't obviously write them all, but you can put ellipses. Right? This is, again, an example of an infinitely stretching system. All right. So I'll put the ellipses here to indicate that it's beyond where I left off. All right. That's how it looks. Right? All right, now we will check the criteria. All right, we want to see if this is again closed. All right, and if it involves the it incorporates an identity element, and if there are the inverses that are appropriate, and 4 if it's associative. Right. You can see why I sort of belabor, trying to explain the intricacies of this, although it is a little bit more useful to you when you use these sort of abbreviations. There's a lot to it. What does it mean to be closed? What does it mean to be an identity element? What are inverses, right? There's a lot of prior knowledge that a person would need to get to this point, right? Anyhow, remember, if it's closed, it's basically asking you, right? This, unique to this problem, does adding the elements result only in more of the same elements? Does adding result only in more of the same elements? Right, that would be that something is closed, right? And you're hoping the answer is yes, but let's see. We're dealing with the whole numbers, right? It would be really impossible to check every possible combination, but you could I would do at least a few to get yourself comfortable, all right? And try to conceive of a situation where it wouldn't be possible, all right? If you can come up with a counter example, all right? All right. You would only need one counter example to say no, right? All right. All right. So, all right. If you added 0 to anything, right, you would end up with those things, right? We know from talking about identity elements, which is another step here, right? So it wouldn't change anything, right? If you use 0 as one of your add-ins, right, you're going to end up with the same elements, all right? So far, so good. If you added 1 to anything, right, you would end up with just a whole number, basically, right? So another way of phrasing this, and this is why it gets a little tricky, does adding result only in more of the same elements? Well, what are the type of elements? Only more whole numbers? Right? Or another way of phrasing it is, what is contrary to the concept of whole numbers? Do you ever get fractions when you do this? If you added a bunch of whole numbers, would you ever get a fraction? Right? No, you'd get another whole number potentially, right? So, is this closed? Yes. All right. It's a little bit hard to wrap your mind around because it's a little alien, but you would say yes. In this case, it is in fact closed. All right, because adding whole numbers results only in whole numbers. Okay, so you would say yes, so far so good. Okay, next thing, all right, is the appropriate identity element present in the set, right? The identity element, right, is 0 present, right, in the set, right? 0 is the one that we need as an identity element because we're talking about what operation? Addition, right? So you would say yes, right? 0 is present, right? Next one. Are there the appropriate inverses? Another way of phrasing this, right? Since we're dealing with whole numbers, are there the appropriate inverses? The appropriate inverses when we're talking about, again, the operation of addition would be basically negatives, right? Which, if we're going to be using a more eloquent phrase, right? The negatives are integers. They're whole numbers, but they have a sign that is either positive or negative or technically zero, right? Well, in the case of zero, right, it doesn't have an opposite sign. It's just zero is zero, all right. But one would there'd need to be a negative one, right? Is there a negative one in the set of whole numbers, right? Right? No, right? So therefore, in this instance, we would say, all right, we've hit a wall, all right? All right, this is not a group. Not a group, because when we got into the situation, the criterion of there being inverses, there aren't any, right? So therefore, not a group. Okay. All right, and there's no point in proceeding once you finally found something that disqualifies it. Zero can be a little bit tricky, so let me take a moment to try to give you some good advice here. I'm just trying to cover all bases here. I'm just going to write this. All right. When it comes to addition, all right, zero is thought of as being its own inverse. Right, and here's why. Right, if the model that we have is any element plus its inverse produces zero, right? This is the model, right, of inverses, right, for specifically addition operation, right? We like to have a situation where we have a positive and we have a negative, right? But pay attention to what the result is for a moment, right? If the element is, in this case, of zero, then there is zero is neither negative nor positive by definition, right? So there really is no sign that we can attach to it, all right? Let's see if this relationship is true, right? All right. Would 0 plus 0 be 0? It would, right? So that was kind of an awkward way of thinking, all right? When it comes to the operation of of addition, all right? Just realize that 0 is its own inverse. Okay? Right, its own additive inverse. In the operation of addition, all right, 0 is its own, I really should use this phrase, additive, right? Even though that seems kind of awkward, right? Because we would want to attach a sign here and we can't. All right. All right. Just keep that in mind. It will be helpful. Okay, when it comes to multiplication, all right, 0 has no inverse. Right, remember the model, no multiplicative inverse. Right, remember the model is this. A times 1 over A should equal 1. Right? Now let's say again that your element in this case is 0. This is a multiplication operation. First of all, does 0 times anything ever produce the number 1? Right? Look at the result rather than the guts in between. All right? Would 0 times anything ever be 1? It wouldn't, right? Right? It's never going to equal 1, right? So even if you took the time and went, well, maybe I'll just put 0 like this, right? That is, you have 0 as something of a denominator, right? Even that is what you would refer to as undefined. Right? You can't have 0 as a denominator. Ever, okay? If you took your calculator and you pressed 1 divided by 0 rather than the other way around, 0 divided by 1, you would get an error message because you can't divide by 0. You could divide into 0 but not by it, right? How come? There's no relationship that would produce this result, all right? So when it comes to multiplication, 0 has no multiplicative inverse, right? When it comes to addition, 0 is its own, all right, additive inverse, right? Just something to be careful of, okay? Let me get some water, pardon me a moment. Let's do example 2. Hopefully this is legible. All right, example 2. I'm just going to again rephrase what is written here. Example 2 in the packet is on this page. Okay. Essentially, the question is asking, is the system, and I'm just kind of trying to emphasize here, the system of the set of rational numbers right, under the operation of multiplication, a group. Is this particular system a group? Right. Again, as a preliminary step, do yourself a favor, maybe illustrate the point. In the case of rational numbers, it might be a little bit tricky, so I might be more verbal than explicit. Right. So here is a preliminary step. Right. How does this look? Rational numbers are quite a lot of things, right? It could be 0, because what qualifies something as being rational is anything that can be a fraction. Right? So in theory, the number 0 could be written as 0 on top of 1. Right? That's not incorrect, because notice where 0 is not. It's not a denominator, it's a numerator. All right? That's one point. Right? If you took an integer like -7, right? Can you make -7 look like a fraction? You can, right? So you would just stick a 1 under it, right? You might just have had a fraction to begin with, in which case a fraction is a fraction, right? What about a decimal? Something like 0.5, right? A decimal number, right, would be the number 5 sitting on top of its place value. 5 in the 10th place is 5/10. You could simplify it also, right? It would be 1/2. Or some combination of that, right? It could have a negative attached to it as well, right? So essentially, what does that mean, right? To be more verbal than to give you specific examples, right? It would be all fractions, you know, in union with all integers. Remember, integers is something that is a positive, a negative, or a positive, or a 0 whole, right? So things that don't start out looking as fractions, but can be made into looking like them, right? Here's regular 11, right? You can make regular 11 look like a fraction real easily, right? And things that are fractions to begin with, like 3/4, okay? So that's basically what it would look like, right? Rational numbers are all fractions in union with all integers, right? Another way of saying it, and this might be more practical as you're sort of plucking this apart, right? If this is what it is, right? All integers, then what is it not, right? Right? What not? Anything that is irrational. Sometimes it's easier to think about the problem from the perspective of what it is not, all right? Why? Because there's fewer things categorized as irrational, right? What's irrational, all right? Pi is an example of an irrational number, right? Because it's 3.14159, and because it is non-terminating and non-repeating, there's no technique that we have to make it transform it into a fraction. In spite of anything, right? Like in your head, you might remember, well, what about 22/7? Good point, but 22/7 is a very long repeating decimal, actually. It's just disguised, all right? It's, let's see, 3.142857 repeating, all right? The decimals after the 3, that is 142857, I believe it is, all right, would have a long bar over the whole thing, and then after the 7 on the end, it would repeat, all right, another chunk. All right, so 22/7, although we've probably used in our lives, you know, 22/7 is an approximate for pi. It's not actually pi, is what I'm getting at. All right, another example would be something like the square root of 2, you know, or famously Euler's number, right? 2.71, whatever it is, into infinity. Something like that. These are infinite and non-repeating. So because they are infinite and they are non-repeating, they can't be a fraction. Right? We can get something very close to them in the style of a fraction, but they will never actually be the thing. Right? So since we have pretty limited examples of this, it might again be, in this instance, trying to answer this question, thinking about it from the perspective of what it is not. Right? That might be helpful. Right? So let's try these qualifications again. All right, we want to make sure that this is closed and that there is the appropriate identity element and that there are inverses for each. And that this is associative if in fact we get down that far. Okay, so, all right, is the system closed? Right, what we would have to say to ourselves is the operation being multiplication, right? does multiplying produce only more of the same type? In other words, if you multiply rational numbers, will it produce more rational numbers? And the answer to that question is, in fact, yes. All right? Yes. Multiplying rational numbers only produces more rational numbers. All right? When you do that, you don't get a situation where you end up with maybe, you don't end up with pi ever, do you? Right? If you multiplied a fraction times a fraction, are you going to stumble into pi by dumb luck? No. Right? If you multiply a negative times a decimal, all right, are you going to end up with some kind of a square root? No. It would have to be those things to begin with in order to somehow have them in the end, or some form of them in the end. Something like a radical might produce another radical, but a non-radical is not going to produce a non-radical. It's not going to produce a radical. All right. So is this closed? Yes, because multiplying rational numbers only produces more of the same. Right. More rational numbers. Right. Now, when it comes to the identity element, all right, the appropriate identity element, all right, would be 1. Right. All right. Is 1 a rational number? Essentially is what you have to ask yourself. Yes, all right? Because you could take the number 1, here's 1, all right, and write it in the style of a fraction. It might seem silly to do that, all right? But if you can take something and then make it look like it has a fraction form, all right, something over itself, a ratio, all right, in this case, right, then it in fact qualifies as a rational number. So 1 would be part of this, even though I hadn't written it, right? It's impossible to write all of them, unfortunately, right? So you would say yes to closed, yes to it having the identity element that is appropriate for multiplication. 1 is the appropriate identity element for multiplication. Then we get to 3, all right? Is there an inverse for each of these, all right? That's a bit trickier, right? Right? And here's the reason why. Right? I alluded to it before. When it comes to 0, and 0 would be considered a rational number, it's under the umbrella of rational numbers. Right? 0 is a rational number. Right? That's the first thing to bear in mind. Right? So if 0 is a rational number, that means that you could disguise 0 as a fraction by sticking a 1 under it. Right? 0 divided by 1 is still the thing that you started with. So everything is copacetic in terms of that. Right? But, right, as mentioned earlier, right, does 0 have a multiplicative inverse? It has an additive inverse itself. But does 0 have, in fact, a multiplicative inverse? I'm sorry, that's very weird spelling there. Bad handwriting, right? I'm worried about a multiplicative inverse because we're dealing with multiplication as the operation. And the answer to that question is no, all right? Because 0 times 1 over 0, even if you could do that somehow, is not going to equal 1, all right? This isn't even allowed. This is undefined, right? If 0 could be written as 0 over 1, then in theory, to write it as a reciprocal would be to put the 1 on top. But trust me, if you ever try to do this with your calculator, that is, you hit the number, then division, and then 0 as the denominator, you get an error message, right? Because you can't divide by 0. Right? So this being not possible, a mathematical impossibility, 0 times anything is never going to produce anything other than 0 anyway, right? So it's not possible, right? And this is where we hit a brick wall again. Is there an inverse for each? No, right? Because it's 0. Right? So is this a group? It is not a group. Again, it's not a group. That thankfully spared us from having to check every possible combination of rational numbers. That would be impossible anyway. All right, we die first, right? All right, one more of these. Example 3. The only difference between example 1 and 2 and number 3 is that number 3 asks you to go the whole 9 yards, which is to check if something is commutative. All right, so far we've only had the standard groups, all right, not the extra criteria group. All right, so example 3, if I'm just going to rephrase it, again, as a teacher, never be afraid, all right, that you can take the material given to you and make it better, all right? What do they call that? Self-efficacy, I believe is the phrase, all right? If you have a lot of experience with something, you get better and better, all right, at trying to rephrase it in a more clear way than it was given to you even, all right? So try to do that, all right? Is the system and the system would be comprised of a set and an operation, real numbers, you know, which is often symbolized by that Gatsby-esque kind of R. Under addition, that's the binary operation, a group, and specifically a commutative group. And I hope that that's clear. All right. Is the system, this particular one, a commutative group, which means we have to check, in theory, 5 requirements, not just the 4. All right, so far we've lucked out. We only had 3, and they blew up in our face anyway. All right, so we're gonna do the preliminary thing, which is try to illustrate how it would look. The set, at least, right? If we're dealing with real numbers, that's basically everything. I'm sorry, I kind of erased it. It looks so nice to begin with, and I screwed it up. All right? All right. Gatsby-esque R. All right? Party animal over here. My sister is drinking. Milk, I swear. But out of a container. I feel you, man. All right, so back to reality here. Real numbers are virtually everything. All right, so rather than do exactly what I had done before, you could, and I would never fault you for that. All right, but it's sometimes, again, it gets easier and easier to refer to something, refer to what it isn't, because there are fewer examples of it. So everything, right, that isn't imaginary. You may not remember what an imaginary number is, but an imaginary number would be a situation where you have a negative that is not imaginary, is what is real. This is the example of what is imaginary. Right? It's only just this one thing that you really would have to look out for. Right? What is imaginary? That situation where you have a negative underneath the square root. Right? Right. So look for that. You have that one isolated example, really. All right? Let's see if we can completely avoid that. And check our criteria again. All right. Number 1, all right, is the system closed? All right. Number 2, is the appropriate identity element included? Number 3, is there an inverse for each? All right, number 4, is something associative, totally associative? 4. All right, and then 5 is it in fact commutative as well? Now there's kind of a cheat on this, right? And when we get there, I'll tell you, I'll point it out. All right, I think the earlier concepts are pretty, they're difficult to adapt to, right? So don't feel bad. All right, is it closed? In other words, the operation is adding, right? Does adding each of the elements result only in producing more of the same type of element? Now, if the type of element is that you're dealing with virtually everything that's not this, all right, would adding real numbers produce more real numbers, right? Would adding real to real equal something that is real? That's essentially the question. Does adding real numbers produce real numbers? Does adding real numbers ever produce an imaginary number? Right? No, right? You're never going to get a square root of a negative by adding real numbers. Right? It might come from subtraction. I mean, that's another story, but right? Not when you're adding. Right? So is this closed? Yes. Right. So far so good. Yes. Right? It only produces real numbers. Is the appropriate identity element included? Remember, the appropriate identity element for adding would be what? 0, right? Is 0 a real number? It is. So you would say, yep, yes. All right. Inverses. Are there inverses included for each? Right? In theory, right, because we're dealing with adding again, 0 is not a problem. 0 is not an issue in this case, right, because the inverse of 0 is considered 0 itself, right, so that would be fine, all right, and anything else that we can conceive of, all right, an additive inverse would just mean anything that with a negative sign, right? Right. Anything negative, all right, the inverse would just be the positive incarnation of that. All right. By definition, real numbers include the integers, all right, so the whole numbers that are negative are positive, and also the rational numbers, that is anything that can be a fraction. So if you had a fraction that happened to have a negative sign on it, it would still qualify as being real, all right? Again, the only instance where you have really to look out for would be that there's a square root of a negative. Or in theory, the square root of something that would be a positive, an even index, but that's not going to be an issue. Okay, so you would say yes, all of the inverses, in theory, would exist for real numbers. Right. I guess what you could say to yourself is this, not to jump the gun too much. When you're down in the bottom rung of the family tree of numbers, which would be like the integers themselves, right? Then you have to be a little bit more careful, all right, when you're looking for specific examples to meet these requirements. When you're very high up, right, and you're very general, not so specific, bottom is specific, higher up, like real, as in the hierarchy, the label for real, it's a catch-all of a lot. So you could, you're a little bit more safe when you're answering these questions because real encompasses so much, right? Now, when it comes to associative, and commutative. Right? We've gotten finally over this hurdle of the inverses. Right? Why? Because we're adding in this case, not multiplying, so 0 is not really an issue. All right? These two things you can take comfort in knowing for a fact. All right? Is it totally associative? That's a difficult question, right? If you were going to try to do every possible combination, because you can't. You'd be spending the rest of your life and you never finish. But by definition, all right, the associative property is true for all real numbers. I'm sorry, my mark is dying. By definition, the associative property is true for all real numbers. We're not talking about a subcategory here, right? Right? It's by definition true for all real numbers. All right, under the operation of, again, addition. All right. And then we go, okay, well, that without having to check every single one, the definition qualifies. All right. What about commutative? Again, this is kind of where it's a cheat. All right. By definition, right, the commutative property of addition, there's one for addition and there's one for multiplication, of course, is also true. All right, for all real numbers. So we circumvented an issue by taking advantage of some fun factoid from way back. All right? Let me point at something just to give you maybe a little bit more security. All right? That information about associative and commutative, those properties insofar as our textbook is concerned, right? This came from section 5.5, all right? It is established fact already. All right, the definition of the associative property of addition, the definition of the commutative property of addition is specifically for these scenarios, all real numbers. All right. And here's what they look like, right, taken from section 9.1. Right. If you want, right, in the book of math legality here, you could go back to, section 5.5 just to verify. Here, I'll just show you this. I know you may not have a physical copy, but take a look at this. All right. We summarize the properties mentioned in this section. All right. A, B, and C are any real number. All right. So commutative property of addition, commutative property of multiplication. We're concerned with addition in this case. But similarly, associative property of addition is associative property of multiplication. Right? We are interested in addition in this case, but you can take it for granted is what I'm getting at. Right? If they just use the description, what about real numbers in general? You got the definition. The law of math is on your side. Right? You don't have to struggle. Okay? So that's that. All right. Put that away. All right. We're finished. So it's a lot to assimilate. All right. If you feel a little sketchy about it, again, don't feel bad. All right. It's not practical math yet. Right. This has, I am told, practical application in several fields, but not maybe in ordinary life. Anyhow, it's still invaluable to us because it's a mental exercise, and that's why you do anything really, right? If you want to get physically stronger, what do? You go to the gym or you exercise at home, right? And it makes you physically stronger. If you want to get mentally stronger, what do? You confront a topic that is unfamiliar and you try to reason it through, right? That's what makes it valuable. The experience is what makes it valuable, right? So for homework, all right, please try My Lab section 9.1. Right? If you do that, you're all squared away, right? Right. I think it's better to do it in one sitting, right? As I said, it's kind of alien, not to corrupt your opinion, but just do section 9.1, then take a break, right? Don't try to do 9.1, 9.2, and 9.3 in the same sitting. It's kind of painful that way. right? That's why I broke it up according to the calendar over several days, right? It takes some time to get used to it, okay? All right, thank you for listening. I'll see you on Tuesday. All right, be careful out there.